Alright, in this video we are going to look at 3 examples of models using the logarithmic functions and how to solve those applications. Now, one of the things you're going to notice about log models is that a lot of times those application problems are fairly lengthy to read, and they have a lot of information in them that does not is not necessary to the problem. With quite a few logs or log problems, if you were to simply pick out the formula and then read the question being asked, generally you have enough information between those 2 small pieces to solve your problem. However, it is always a good idea to really make sure that you read these questions carefully, because sometimes there is hidden information embedded. So in this problem here, we are talking about that past research tells us our bodies grow at a given rate based on our DNA and the environmental factors in which we grow up. If we assume that a baby girl is born and is 22 inches long, and we consider that the baby will grow at a rate proportional to her body size until adulthood, then the percentage of her adult height attained can be modeled by the following. So it's giving us the function, and then it tells us what's in the function. So x is going to be her age in years between 0 to 25. F of x represents the percentage of her adult height reached at that specific age. So the question wants to know the percentage of the girl's adult height obtained by the time she's 12. So in this case, we are being told that x is 12. So here we are looking at f of 12 is 22 plus 55 log of 12 plus 1. So here we would simply use the log function on your calculator. Again, you can unpack it and work it slow. So if we look at my calculator here, okay, and let me kind of do this a little so you can see it. Alright, so right here is my ln and log button, and so essentially what I have is I would work with the log function first. So I'm going to have log of 12 plus 1 and hit enter. I'm going to multiply that by 55, and then I'm going to add 22. And so in this case, that is how you can work from the inside out, slowly unpacking your log function. And so what this tells us is that we have 83.27% of her height. Alright, let's look at this next one. So the pH of a solution is defined to be the pH equals negative log of your concentration, so the H3O concentration, where H3O is the concentration of hydronium ions in moles per liters. Solutions with a pH of less than 7 are said to be acidic, whereas those with a pH of greater than 7 are basic. If a sample of orange juice is determined to have a concentration of 1.58 times 10 to the negative 4 moles per liter, what is the pH? And then the secondary question, is it considered to be acidic or basic? So the first thing we have to do is we have to identify our parts. So here we have H3O plus, so that's our hydronium ion, and we're telling you that the concentration is 1.58 times 10 to the negative 4. So in this case, to find my pH is going to be the negative log of 1.58 times 10 to the negative 4. So in this case, again, you could use your calculator and you'll come up with 3.801. Now here, since 3.801 is less than 7, the solution is acidic. This last example is going to be about earthquakes. And so if you think about an earthquake, what modern scientists do today is they use the seismographs in order to measure intensity of earthquakes kind of around the world. And when an earthquake is happening, that seismograph starts moving all over the place and starts moving out of control. And one of the things that it's doing is it's measuring the intensity levels. So we can use the intensity level along with this formula here in order to tell you what the Richter scale number is. Now the Richter scale is the number that we all hear. So for example, when the news comes on and says that there was a 7.3 earthquake that struck, the middle of the Pacific Ocean. Well, that number 7.3 is the Richter scale. So it is our way of talking about the intensity of the earthquake. Well, the reason why the Richter scale uses this equation and uses numbers that are a lot smaller is because earthquake intensities can be in the millions. And we're talking about an intensity in terms of millions of times greater than a zero-level earthquake. Well, a zero-level earthquake is essentially the planet today. So if you were to stand up in your room and just kind of stand still and feel, you don't really feel anything happening. But in reality, the earth underneath your feet is moving. Okay, and so we call that a zero-level intensity because, yes, we are moving a little bit, but it is not enough for you to feel it. Now, the more the earth moves, or the more violent the plate tectonics shift around, the more we get earthquakes, the more we can feel. And you actually get to a point where you can really start feeling things shake. And that's when we climb the Richter scale. And the more the earth shakes, the higher the number. Well, what this all boils down to is that you can actually calculate those own Richter scale values if you simply know the intensity. Or you can reverse it, and by knowing the Richter scale number, you could calculate for yourself the intensity of that earthquake. Okay. So in this problem, we are simply going to look at calculating the Richter scale ranking. So in January 2001, there was an earthquake in India, and the seismograph measured the intensity to be 80 million times greater or as intense as a zero-level earthquake. So a zero-level earthquake we register as essentially movement of 1. Okay, it's your initial intensity. And in order to calculate your Richter scale, you simply have to plug it in. Okay, so when we're talking about I, this is going to be the intensity that was measured. Okay, so for example, your 80 million times more. And I naught is your zero-level earthquake. So here, this would become, R is the log of 80 million over 1. And so here you would simply, again, use your calculator, and you would find out that this was a 7.9 earthquake on the Richter scale. So one of the things that you could notice is that the intensity, whereas it was so much higher than a zero-level earthquake, its Richter scale number is only 7.9, which we know is a pretty bad earthquake, but not as bad as we have seen. So that intensity level really does play a huge part, and what you can see is that those numbers get huge very quickly. Okay, so there you have it. That is, in a nutshell, everything that you need to work with different types of log functions in order to evaluate applications. So if you have any questions, please let me know. Otherwise, I do hope you enjoyed, and I'll see you next time.